Good afternoon and welcome to Metal Forming Magazine's second annual Hot Stamping Experience. This year presented as a series of educational and informational webinars, but still featuring a plant tour where we're going to get to see hot stamping in action. That'll be next week, albeit as a virtual plant tour this time. My name is Brad Coogan. I'm the editorial director at Metal Forming Magazine and the Precision Metal Forming Association. And I'm pleased to serve as your moderator today and throughout the webinar series on Thursday of this week and then again next Tuesday. Before we get started, just a few notes about today's go-to session. The meeting and all of the others in the webinar series is being recorded for archiving. The recorded events will be posted to our website at the conclusion of the series early next week, and we'll let you know by email when those recorded webinars are available for viewing online. Also, all the participants in the meeting are on listen-only mode. That means that the speaker and other listeners will not be able to hear audio from your site during the program, but you do have the ability to communicate with us throughout the program by submitting any questions and comments using the question box, which is located on that right-hand control panel on your go-to screen. So you'll simply type your question to an organizer as selected from the drop-down menu, and then you'll use that same panel to ask questions of our speakers at the end of each presentation today. Lastly, before we get started with the presentations, I want to thank our event sponsors, Schaeffler, Fagor, and TJ Snow. Without their support, we would not be able to bring you events like this one. So again, much thanks to them. To kick things off today, our main event sponsor, Schaeffler, has provided a short video for us to enjoy, which has some really excellent clips of the hot stamping process in action. It's a nice way to get things started. So please enjoy a short video from Schaeffler, and then we'll be back to start today's presentations. Help making this event available for us. So it's time to begin today's webinar. We'll begin with a talk titled Recent Developments in warm and hot stamping of steel and aluminum. Our presenters are Eren Billur, Technical Manager with Billur Metalform, and Danny Schaeffler, President of Engineering Quality Solutions and Chief Content Officer of 4M Partners. Both Danny and Eren are regular contributors to Metal Forming magazine. I hope you see their columns on a regular basis in the magazine. So Danny Schaeffler specializes in solving sheet metal formability problems and in material selection and optimization. Danny works with global automotive and non-automotive OEMs and their suppliers, as well as steel and aluminum producers and their service centers. And Eren Billur graduated and received his PhD in mechanical engineering from Ohio State University in 2013. As a researcher at the Center for Precision Forming there, he was responsible for the coordination of sheet forming research. Eren has authored or co-authored more than 20 scientific papers and has contributed to 4 books, including a book called Hot Stamping of Ultra High Strength Steels, which was published in 2018. So without further ado, please welcome Danny and Eren.
All right. Good afternoon, everybody. This is Danny Schaeffler, and I'm going to be leading off just with a handful of introductory slides. Today's talk over the next half hour, 45 minutes, we're going to be covering many aspects of the latest and greatest having to do with press hardened steels, as well as warm and hot forming of aluminum alloys. We're going to cover the material aspects, what, where and how it's being used in automotive applications, and some not just novel materials, but novel processing routes for optimizing how these products are used in automotive body structures. As I said, we're going to cover warm and hot forming of aluminum on PHS lines, as well as give our thoughts about where the future lies for warm and hot forming of both steel and aluminum. Each form part in a body structure plays multiple roles, balancing customer preferences against global regulations for safety, fuel economy, and emissions, all while maintaining an affordable purchase price. There are actually over 250 stamp parts in the body in white alone, while if you consider powertrain, chassis applications, seats, and so on, there's over 600 stamp parts in a vehicle, each of them having their own properties of stiffness, formability, the need for strength, energy absorption capability, as well as, depending on where it is in the vehicle, the need for corrosion resistance. It's critical that the right material is used for each application and the needs of that application. For example, you have skin panels which require dent resistance and formability. The safety cage that needs intrusion resistance, and there's a lot of applications for PHS steels there. And you have the front end structure where energy absorption is required, and each of these for those properties requires a different steel or aluminum grade. There are many many products that are currently available on the market that can have those properties tailored for specific applications, be it energy absorption, formability, dent resistance, and ideally springback minimization for processing ease. We'll be discussing PHS applications here, but there are new grades on the horizon, which will also find ways into automotive body structures. regarding PHS, the base steel that is used is sometimes referred to as an MNB, manganese boron alloyed steel, and comes from the steel mill as a ferrite perlite product or product that has that microstructure. And that's where the indirect process is used. We'll be learning a little bit more about that in a handful of slides, but it's used in that condition. But for direct press hardening, the product you get from the steel mill is put into a furnace for a short number of minutes, heated to typically over 900 degrees C to change the microstructure to austenite, and then rapidly cooled at a minimum of 27 degrees C per second to create the press hardened structure with a martensitic microstructure. After that quick intro, I'm going to turn it over to Eren, who did a lot of the work compiling the information in the next couple of slides.
Hello, everyone. I think I should say good afternoon. It's almost 9 p.m. here, but I think it must be approximately 1:44 in the eastern US. So in this slide, I'm going to show you PHS record setters. PHS has been used in the automotive industry since 1980s, and there has been a few applications in 1990s and 2000s, but one of the record setters was Volvo XC90. It's not the first car to have its B-pillar hot stamped, but it's one of the first cars to have a significant amount of its car body, 7% by mass of the body in white, in hot stamping. Throughout the years, there has been a VW Passat. I used to own one of these because I didn't want to contradict with myself. I still think it's one of the safest cars on the road. It had 19% of its body in white as hot stamped, and it has been in sale since 2006 to 2014 with some minor facelifts in Europe, but in the US after 2012 you received a different version. From 2006 to 2012 there has been many cars that had significant amount of hot stamped components, but they have never surpassed 19%. In March 2012, the first car I saw to break this record was Volvo V40, but it just held its crown for a few months until we see the Audi A3. Now this is the old version, by the way. There's a newer version in 2020 that has 29% of its body hot stamped. And then in, I think, August or September, the Golf 7, which is again right now the older generation, was rolled out, and it had 28%. And after that, couple years after that, we have seen Volvo XC90. This car has all this red colors and some of the yellows, and you will see more in detail, is hot stamped. Actually, 38% of its body in white is hot stamped, but there's a small star here. 33% of it is the PHS grade, and 5% of it is a PQS grade, which I will talk about. And talking about the markets, in 1980s, all the components were limited to door beams. So in a car, a maximum would be 4 parts per car you can get, and the production was limited to about 2 to 3 million parts per year. By 97, we have seen several cars bumper beams, not yet A-pillars. The first A-pillar was, B-pillar. The first B-pillar was in Peugeot 307. That's a French compact hatchback car, similar to VW Golf, and that was in 2001. And then we started seeing a lot of components being hot stamped. Here you see all the hot stamped components of VW Passat. That car, including its door beams, had about 11 or 15 parts if you consider bumper beams and door beams also in the body in white. And the production has risen to 85 million parts per year. By the way, this is not a must, but it typically holds. It's a rule of thumb. You can consider the number of lines around the world approximately by the million parts per year. So in 1980s, I would say there are only 3 lines or 4. By 1997, there would be 8 to 10 lines. By 2007, the number of lines have already increased to 80. In 2015, we have already seen a number of cars with more than a quarter of their body in white hot stamped. The number of parts increased over 15, parts production increased over 300 million, and by 2015 we already had more than 250 lines around the world. And in 2018 this number is slightly lower than that. I would say 550 million parts per year. This is from my book, it's slightly old now, but I can tell an average car now has about 10% of its body in white hot stamped. Here we see the press hardening steel, because since 1984 to about 2011 there was only one grade, which is called 22 MnB5, and throughout the last decade we have seen several improvements in either having higher strength or having higher elongation or higher energy absorbing capacity. Let's put it that way. So once again, since the start of hot stamping industry, we only had 22 MnB5. There was only one chemistry, but now we have a total of 5 different levels, and you will see several other grades, 20 MnB8 and 22 Mn silicium boron 95. I'm sorry for that long name, but we now have 3 different chemistries that can have about 1500 megapascal, which is about 220 ksi tensile strength. The second steels that we have developed is called, now we call them as press quenched steel. They are quenched, but they're not hardened. So we have 6Mn3 and 6Mn6. You might have heard different commercial names like Ductibor for these grades, or MBW 500 or MBW 600. These are the energy absorbing grades. Then in 2011 we started seeing PHS 1800. These are higher carbon grades, and very recently there's a 20 Mn CR. This is an uncoated blank having about 1700 megapascal tensile strength. Then comes the 1000 or 1200 megapascal grades. These are the most recent ones. At this point, I have heard there are several cars having these grades, but I don't have a reference for that, so it's just a saying for now. But we will talk more about, especially about this 1000 and 1200 megapascal grades. And at the top of the crown we have PHS 1900 or 2000. These have the two numbers, the first 2 numbers that you see shows us the carbon level. So they have the highest amount of carbon, about 0.34 or 0.37% weight percent carbon. By the way, all the stress strain curves are approximate and may change significantly from batch to batch or by the cooling rates. So in most resources, you would see there are 2 process routes, direct and indirect. This has been almost correct for a long time. And when we are looking for the process routes, what we should be taking into account is the operations. So we have blanking or cutting to length as one operation, heating as another operation, forming, cooling, quenching, and trimming, piercing. And by changing the route, the operations orders, we can get to different processes. As of 2020, there are a total of 10 different processes that I will go through very quickly. Now, when I put these 5 operations in the order, in the direct process, we have blanking, then we heat the undeformed blank, we form and immediately quench it, and then we take it to laser trim and pierce typically. In the indirect process, we blank and in cold form, then we cold form and do the trimmings and piercings as well. Then we heat the already formed and pierced part, quench it, and in most cases we need to do a surface conditioning, which could be sandblasting or similar. And you might have heard 2 different names for direct and indirect process, especially in German language and translations from German. You might have heard press hardening. This is what we use also for PHS. And there's another word called form hardening. I have been to a handful number of lines, and I have only seen 1 form hardening line until now. So around the world, we can say maybe 95% of the lines are for direct process, maybe 5% is only for indirect process. That's why we don't say form hardening steels. The main difference between the direct and indirect process has been the coatings. So we heat these blanks over 900 Celsius, and when you have the aluminum silicium coated blank, the problem is you would have the melting of aluminum silicium coating, approximately around 600 degrees. And this would cause a lot of problems if you have a roller hearth furnace. Your rollers may be contaminated due to this melting, and you could have a lot of maintenance issues. The reason we select direct process with aluminum silicium coated is because if we cold form them, the coating breaks. And with the zinc coated ones, we have several problems. One is zinc melts around 420 degrees, and the second is it vaporizes around 906. So the austenitization temperature is about 885. I have to have a very narrow process window. That's number one problem. And number two problem, if I have liquid zinc and then form the part, I could have some micro cracks. By the way, I don't know if you can see my drawing here, but this is the zinc coating and this is the base metal. If I hot form while there's liquid zinc, that zinc could go inside the base metal and cause some macro cracks. Now, I said 10 different process routes. Let me go very quickly over the other ones. There's one I call as hybrid process. Here we make blanking, make a first forming, heat the already formed preform, make a secondary forming, quench, trim, and surface condition. This was the first method to make deep parts, such as the transmission tunnel. And as you can see, the total depth is maybe 2x. Here I have a part, a preform that's only half deep drawn. But since 2010, 2011, this process has been vanished around the world. It's not used anymore. As I said, the problem with zinc coating is if there's liquid zinc, it can go inside the base metal. And there has been a number of studies. What would be the problem? How many microns of the crack going inside the base metal would create problem? And it looks like if you have a micro crack that goes only 10 microns deep, like this one, it's not really changing your fatigue life significantly. But if you have anything over that, then you can have, if you take a look at this one, we have less than 200 megapascal as the finite infinite life, whereas here we have more than twice of that. So most OEMs limited their acceptable micro cracks as
Uh-oh, we lost Eren.
could happen if we.
Oh, he's back.
I'm sorry?
We lost you there for a couple seconds, Eren. I'm not sure what happened.
Oh, I now see audio connection is restored. Sorry
Okay,
for that.
you're back. Nope, it's all good.
Okay. So here we are seeing a part similar to a bumper beam and the micro crack depths with direct forming of zinc coating. As you can see, our threshold was about 10 microns and we have a number of cracks over that. This new generation steel that can handle a pre-cooling, where we take it from 900 degrees and we put it in a pre-cooling stage and cool it to approximately 500 Celsius and then form. And what happens then is, as you can see, with pre-cooling, we have only 2 micro cracks and they're well below the threshold that most OEMs are putting. But for this, we need a special so-called conversion delayed alloy, and it's called 20 MnB8. This is developed by voestalpine. I have the references down there. So what do we mean by convergent late grade? Remember we talked about critical cooling rate for the typical steel, 22 MnB5 as 27 Celsius per second. This is, by the way, logarithmic. This scale is logarithmic, as you can see. If I can cool it more than 27 Celsius per second, I have almost always the same hardness. For 20 MnB8, this number goes down to 10 Celsius per second. But the typical process route is to ostentize it as at 870, cool to 500 at over 20 Celsius per second, transfer within 7 seconds, and once formed, quench it at over 40 Celsius per second. And then we have this new air quenching grade. And as you can see, even at something like 1 Celsius per second, I'm still having almost 450 Vickers. And this allows us to use this grade in a transfer press. And in this case, I can do the forming and trimming. Even I can use cams to make pierces on the wall. And this is called a multi-step process. Right now, to my best knowledge, this is in use in mass production for a German compact car in Europe. And I don't know if there's any other car right now using it. This is an information from last year, 2019. And if we compare all these PHS grades, again, all stress strain curves are approximate and they may change. Don't judge them and say 20 MnB8 has a longer elongation. Depending on the cooling rate, these may change significantly. But as you can see, all three would have approximately 1000 megapascal as their yield strength, about 1500 megapascal as their UTS. Now, there are several other process routes for profiles and tubes. One is called the roll form PHS. You can roll form as the 22 MnB5 or a similar steel, induction heat and water cool it, and then cut to length and trim and pierce. This is already in use for many years as well. There's a technology called form fixture hardening. The difference here is you roll form the part again, you cut to length, then furnace heat, die quench, and trim and pierce. Hot gas metal forming or form blow hardening. Now we have tubes, we cut to length, we heat them, we form them by inner pressure and quench and pierce. There's a technology called three-dimensional hot bending and direct quenching, abbreviated as 3DQ. You cut to length the tube again, induction heat it, you make a 3D bending and water quench, and if necessary, pierce. And the latest one is STAF, steel tube air forming. You again cut to length, you make a cold preform, and I will show you the advantage of that. You heat, pressure form the part, quench, and pierce. They look all similar, but there are slight differences. That's why I'm putting them as separate process rules. Now, what is relatively recent, I would say, is tubular PHS components. In fact, we had tubular PHS components for many years. This is again a Peugeot 307. I said the same thing. I said the first B pillar was in 307. That was the hatchback version. Here you are seeing the convertible one. And you would see the A pillars were tubes, but they were not really pressurized. Right now, in the last 2 years, we see a lot of cars, and it looks like the upcoming new Ford Bronco looks like, again, I'm not 100% sure yet, but it looks like it has a hot stamped boron tubular roll cage. This is the new Ford Focus, fourth generation. I think you don't have it anymore in North America, but it's quite popular in Europe and China. So this vehicle has a tubular A pillar, as you can see, with a number of brackets and other parts welded to it. And what is really interesting in this one is that it's a tailor rolled tube with different thicknesses, and it's pressure formed, hot blow formed, so it has different cross sections as well. And this is in mass production for a compact car. It's not a luxury or a high-end vehicle. But I have to say also in other regions, it may be monolithic with 1.6 millimeter thickness. But in Europe, it's at least for now, it's a tailor-rolled tube. This is the direct competitor, in my opinion, of Ford Bronco. That's Jeep Wrangler. You see the 4-door and 2-door versions, and there's a common front bar. This is a common part both in 2 and 4-door version, but depending on what you have as a 4-door or a 2-door, you have a different rear bar. These are also hot blow formed tubular components, and this is in production for only 2 years now. Another car with tubular PHS component is, I think this is called Acura NSX in North America. It's also known as Honda NSX in other parts of the world. It's A-pillar, and in fact, it's almost like a cantrail all the way to the back. It's a 3DQ formed, so it's a tubular part, only heated and bent. There's no pressure forming in this. And here I'm showing you the latest tubular PHS technology called STAF. So when you make hydroforming, by the way, I would say hot gas forming, because hydro by name it says as if there's a liquid. We cannot make liquid hot forming, so it's hot gas forming. When you have hot gas formed parts like the one we have seen in Focus and Wrangler, you don't have the flange to weld other parts. So with STAF, what they do is you get the tube first and you cold preform it to have some flange area, and then you hot gas form it. So it has the advantage of having a flange, but still having a tubular component with no spot welding. This is a relatively recent technology. I have heard it in 2019, and to my best knowledge, this is not in mass production as of today. By the way, I may have some outdated data. If you know it better than I do, please let me know through the Q&A. I would be very happy to update my slides. As I told you, I wanted to talk about PQS, press-quenched steels. When I say press-quenched steels, I'm talking about grades that has less than 1300 megapascal yields, UTS. And in Europe, they're really hot topic right now. But if you take a look at these two, you would notice that PQS 1000 does not offer any better elongation than PHS 1500. They look very similar to each other. Then how can it absorb more energy? So in the recent years, we have found out that it's not only the total elongation that shows how much energy can be absorbed by a component. Here you see a 3-point bend of a hot stamped part, and at 90 millimeter stroke of the crash, you would see cracks are forming. So its structural integrity is already broken, and it cannot withstand the load anymore. And here you see PQS 1000 at 120 millimeter stroke of the crash, and there's no crack formation. And once again, their total elongations are pretty close. Now, if you take a look at something like this, when a part is absorbing energy, it bends. And it doesn't matter if it's an anti-intrusion part or it's a crushing part, it always bends. So around 2009 in Europe, they noticed that if they make a very sharp bending test and see what would be the angle at fracture, the outer angle at fracture, that would show the crash performance better. And I have to warn you that VDA bending angle, I will show you the test. This is the test, by the way. Here we have a radius of 0.2 millimeters. It's a very sharp bending, like a knife. Now, this is called a VDA bending angle, and it's now a standard requirement in many OEMs spec sheets, including the North American ones. And now, if you take a look at this, instead of the famous banana, here's a new banana curve. I put the yield strength, and as you will see, it's from 950 to about 1200. And then we have the new grades, and PQS 1000, it has almost similar yield strength, and it can be bent to about 1.5 times larger angle. And PQS grades, by the way, they are like 2 or 3 times more bendable than the PHS 1500s. Now let's focus on PQS 450 and 600 of this range. These grades at first were developed to make tailor welded blanks. Here you see Volvo XC90. I would like to remind you this car was the record breaker still with 38%, but I said 33% was PHS 1500. And here you see the other 5% of PQS 500 grades in the rear side members, lower part of the B pillar and the front rails. This was the original idea of PQS. That's how it has been used for many years. You might have a tailor welded door ring, but you would still have this area from PQS grades. That was the main idea. But in the recent years, we have also seen cars with PQS components. Here we see the C-Class Mercedes. It's still in production, the latest generation from 2014. The pink colored parts, like the A pillar all the way to the back, is a PHS 1500 and fully hardened. We also have several components in the floor and also for steering wheel. Then we have the yellow parts, like the rear rail, and I think this is called cowl part. It's a tailor welded blank with PHS 1500 and PQS 550. Then we have the B pillar, which is a partially hardened with soft zones PHS 1500. But what is interesting to see is that we have several parts, like the heel piece, and maybe I would call it as a firewall. I don't know if there's a better wording for that, but this part right here, and this is called heel piece, at least in Europe. I don't know if there's an American saying for that piece. These are made entirely from PQS 550. Another idea that has been recently developed in Jaguar I-Pace is if you take a look at the B pillar. By the way, the car is almost all aluminum. There are several steel brackets. As you can see, all the blue is aluminum, all the green is aluminum skin panels. Then we have several brackets, etc., from steel. And then we have the B pillar from PHS 450, as they name it. So this is a patchwork blank. We have PQS 450 as the master blank, and we have PHS 1500 as the sub blank. The main idea here is that when I'm spot welding this B pillar to the body, I'm always spot welding in the soft zone, soft part. And now in Europe, people are speaking about making this as PQS 1000. So the whole B pillar would be a PQS 1000 with a patch of PHS 1500 or something more than that, maybe 1800 or 1900, so that all the spot welds will be on the soft area with the lower carbon area with less problems. Speaking of PHS 1800 and more, this is the bumper beam from Mazda CX-5. This is an almost 10-year-old technology now. If you had 1.6 millimeter thick PHS 1500, this is the force versus stroke you would get. Here you see the PHS 1800 in the same thickness level. You would have about 25% increase in the peak force. And with the black now you're seeing PHS 1800 in 1.4 millimeters. So we could save about 12.5% by down gauging. But 1800 megapascal was only used by one OEM, Mazda, until last year. Now we see more in Europe, especially with electric cars, some 1900 megapascals or similar. This is the new Volkswagen ID.3. That's the electric Golf size car, VW Golf size car. And you would see there are two seat cross beams. And as there's no transmission tunnel or exhaust tunnel, they're one piece cross beams, and they're MBW 1900. This is the ThyssenKrupp's brand name for the 1900 megapascal grade. And there will be one concept for all the platform. Now we are also seeing the ID.4. That's a small crossover SUV coming up. Most probably, it also has 1900 megapascal in its underbody. With that, I'm almost done with my hot stamping, and I'm going through the aluminum very quickly. If you want to take a look at the latest metal forming magazine, I have this paper there about how to warm and hot form aluminum. This will be a summary of that. Very quickly, aluminum alloys, there are 4 different grades that we use in automotive. 5000 series are really formable. They have corrosion resistance, and we have several grades that we use in automotive, but their problem is they have a surface problem They don't look good when they're painted, so we typically use them in the inner parts. Then we have the exposed series of 6000. They have no problem with painting or surface condition. They can be hardened through the paint bake cycle, which is good, and they're still formable enough. And then we have several special 6000 grades that have high strength and good ductility. And then we have the 7000 series, which is aluminum and zinc, typically called as aerospace grades, but there are several automotive applications in the recent years as well. So one of the first applications of warm forming of aluminum was done at Jaguar F-Type. It's still in production. The door inner of this car is deeper than 165 millimeters. In the previous version, it was an assembly of cast parts and sheets and etc. But in the new one, it's a single piece warm formed part at around 200 and 250 degrees. Another warm forming application was BMW i8. The door beam of this car was 7075 T6 as the incoming blank, but its heat treatment is slightly deteriorated to 400 to 480 megapascal yield. It's softened. Another hot forming application was in a very low volume car, Alfa Romeo 4C, and you would see this floor panel that was formed from 16 1.5 millimeter, and it was formed at 450 Celsius in a PHS line. Another very recent hot forming application is from Aston Martin. In fact, in DB11 that was rolled 2 or 3 years ago, there was only the A pillars were hot formed aluminum. Now in the DBX, there are a total of 9 components, A, B pillars, and roof rails done by 6082 T6. One of the cars with most hot formed components, aluminum components, is a Chinese electric SUV, Neo ES6. And this car has a total of 7 components, 7075 T6. That's one of the strongest alloys and tempers. And very interestingly, they're using only 2 die sets for this 7 different parts. And here you can see all these parts are 2 out. So in this die set, they can get 8 parts out, and in this die set, they get 3 parts out. So for the whole car, they only need 2 different die sets. And last, this is not heat-assisted forming, but since 2012, what we're also doing is we cold form aluminum 6000 grades, and then we post-form heat treat them. And this has been used in Ford F-150 as 26% of the cab weight from PFHT grades, 6000 series with very, very high strength. It can exceed 300 megapascal in yields. That brings me to my final slides. There used to be only one material for hot stamping. Now we have 13 different materials plus aluminum alloys that we can run through the same lines with slight modifications, of course. Productivity, which I mean by parts per minute, is increasing and costs are decreasing, making hot stamping even more competitive. There are many new grades for cold forming with high strength as well, especially like Gen 3 steels. This is one of the minuses for hot stamping. But in Europe, hot stamped steel usage is still expected to increase. And I would say in North America and China, electric cars are increasing, so warm and hot forming of aluminum may increase in these markets more than in Europe. With that, I'm done. If you have any questions, I will try my best to answer them.
Excellent. Thank you so much, Eren, and also Danny as well. We'll take a few questions if anybody has them now, or we can move on to the next presentation. But if anybody has any questions for these guys, and I'm sure you guys are going to stick around until the end of the next presentation as well for questions.
Of course, and if there are any questions, they can also write to us directly. I'm showing our email addresses and contact informations as well.
Yep, excellent. Feel free to email these guys. I guess this is for Eren or for Danny. third generation advanced high strength steels, starting to see those out in the market. How will the use of third generation high strength steels, I guess, kind of compete with the press hardening process or pH press hardening steels?
Let's take a look at here. Here we see different grades of Gen 3. That's where they are right now. It's a very tricky question. With Gen 3 steels, the steel is more expensive, but we consider the process to be more cost efficient. It's a really tough question because there are several studies that shows we can make parts up to 1200 megapascals, but I still don't see any complicated parts over 1300 megapascals. Am I correct, Danny? Do you have any additions to that?
No, but I guess building on what you said, safety cage components typically are going to require the highest strength possible and the associated down gauging that might be associated with that. So I think you show quite nicely the transition around UTS of 1600, that there aren't third gen options that appear to be better than press hardening steels from strength alone. The other thing to keep in mind is the complexity of the alloy that's needed. Only a very, very, very limited number of steelmakers around the world are capable of producing the third generation steels, where the base material for most of the PHS grades are a common enough, at least medium strength ferrite perlite steel. So there's the availability question that also comes into play.
Good, thank you. We want to try to stay as close to on schedule as possible, but I will take a couple more questions now, and then we'll save the rest for later. What do you guys know about computer modeling or simulation of hot forming processes? Where are we at with that technology?
Speaking of stamping of it, I think we can do all these different process routes. From my point of view, I have never simulated the roll formed processes, but that might be my bad. Maybe there are people doing it. I think we can do almost all of these simulations on computer. The problem is, now that we have 13 different grades, as I showed you, we need 13 different material cards to do all these simulations. Typically, we have 22 MNB5 has been around for 30 years. We have all that material card available in most commercially available software. The problem might appear once we go to 1000 grades or 1800 grades, especially with the slight changes with the chemistry, the whole thing may change significantly. So we have to be very careful with what material card we have in our simulations. And I think other than that, we should be, if we are careful with the process and material card, we should be all fine.
My 2 cents on that is that roll forming simulation isn't really significantly different. If you can simulate the roll forming process, then there isn't an issue, to build on what Eren said. But also, I think the process simulation is critical to reflect reality. For example, if there are any gaps between the sheet metal and the warm tooling, or if there's an oxide that's present, you may not be modeling the critical cooling rate properly. If the simulation can match reality and vice versa, then it is going to be very accurate. But in any case, simulation matching reality is a challenge in terms of friction around the part. For example, throw in the thermal component, it amplifies the challenge. But if you can match reality in the simulation, then there's no issue.
That's what I was trying to mean by correct process modeling. So
There you go.
what you have on the computer screen must match what's on the shop floor in terms of the geometry and process forces, motions, etc. If you have anything that's not reflecting the reality, then you are always getting some results, some good pictures, but not really meaningful results.
Yeah. Okay, good. I'll give you guys one last question, and then we'll get Mike going. Preference for the mill source of hot stamp steels in terms of a traditional slab, or thin casters like the Nucors and Tatas of the world. What are you guys seeing any trends and where this material is coming from?
I'm not sure it matters.
Oh.
If it meets the material specification in terms of chemistry and it has the correct dimensions, flatness, tolerances, and so on, I don't see there being a significant difference. There'll be a difference in some of the residual elements, but if that doesn't affect the critical cooling rate, then it shouldn't matter.
Right.
I'm not a metallurgist, so I'm taking Danny's words here.
Okay,
I play
good.
one on television.
Excellent. All right, guys, I appreciate the presentation. I think everybody else does as well. Very informative. Stick around, and there are some more questions coming in for you guys. So after this next presentation, we should have time to address a few more of these questions. There are a few questions being asked about dies and tooling specifically for hot stamped, and I think our next presenter will be able to address some of those questions as well at the end of his presentation. So again, thanks Danny and Eren for getting us going. This next presentation then addresses tooling and die development for hot stamping. Our presenter is Mike Austin. Mike is the Director of Manufacturing Engineering at Diversified Tooling Group, which is a group of companies that includes American Tooling Center, which is a company that supplies hot stamping dies to automotive OEMs and their suppliers. And in fact, Mike's company, American Tooling Center, will be the subject of our virtual plant tour next week. So Mike has 47 years of industry experience in automated processes for hot forming and cold stamping. So please welcome Mike Austin.
Good afternoon. Thank you for attending this session. Hopefully we will get you back on time here and finish before 3 o'clock. I'm coming to you today from Diversified Tooling Group's Technical Center, Midland Design Service in Madison Heights, Michigan, the Metro Detroit area. We're going to be covering tooling and die development for hot stamping today. Before starting, I'd like to briefly just explain our company, Diversified Tooling Group. Although, as Brad said, you'll find out a lot more about us a week from today at 3 o'clock. Diversified Tooling Group has 3 core businesses. It has tooling, as you would imagine, all sorts of stamping tools, prototype tools, cold stamp, hot stamp for structural parts, major body panels, body sides, as you can see here. The second part of its business is low volume production of stampings and assemblies for the automotive market, as well as the Class 8 truck market and other types of vehicle structures. The third area is the defense business. You'll learn a lot more about our company next week. The Superior Cam company primarily started as a prototype supplier. Today it does major prototypes for the automotive OEMs, as well as a low volume production using single operation presses combined with laser processing to make body panels, very low volume production parts, as well as service parts and assemblies for the automotive industry. Midland Design is a metal forming engineering and simulation and feasibility company for both cold and hot stamping processes. In addition, it's a major die design company We sell our die designs to OEMs and to tier ones, as well as other tool shops. And it specializes in both cold and hot stamp dies, both prototype as well as production and various levels of production, low volume, medium, and high volume. Best Pro Pattern is our pattern shop, which makes a lot of stamping die patterns for our own use and for our customers' use. It also is a one-off or two-off or three-off foundry pattern supplier for things that are entirely non-automotive, oil and gas, defense business, you name it. If it's big and it has to be precisely made, Best Pro's made it. American Tooling Center, Grass Lake is our tool and die operation. We have 3 facilities, one in Grass Lake, Michigan near Jackson, one in Jackson, and then a 3rd facility in Lansing, which is where we do the lion's share of our defense business. So we'll be talking today about, or in this webinar series, about the press hardening process. And as you can see here, this is the process that we use at our facility in American Tooling Center, Grass Lake. This is a 2015 automated production press cell. It's very similar to a normal production cell. It has some limitations in furnace capacity, and it has manual loading to give us a little bit more flexibility. Because we use this primarily for low volume production with high flexibility, very short runs. We also use it for die tryout of various types of dies, production dies that we sell to customers, production dies that we use ourselves, as well as prototypes. And we do a lot of R&D work on this cell as well, supporting the industry with hot stamping. So the PHS process, as was explained, is a little bit unique because it's a combination of hot forming, which the heat makes it easy to form the parts, and heat treatment, because we're going through phase transformation from austenite to martensite and creating a very tough and strong part, the strongest part in the industry, in one step. So this is actually the first cycles that we ran on our press cell in 2015. We had been involved in the process for 3 years prior to that, but we, based upon the success of that, we made this investment. What you're seeing here are Taylor rolled blanks. So the center of these B pillars is actually a lighter color. It's white hot compared to red hot on the outer edges. And that's because of the difference in emissivity coming off of those and the amount of heat stored in the blanks. But Taylor rolled blanks are very difficult to run materials. You have to manage a lot of different variables. But this cell has run very well for us over the last 5 years. We're looking forward to many more years of low volume production and use for development. You can see here a B pillars actually being pulled down into the locators on the in the die area and pulled down by the transfer mechanism. The material itself, once it's heated to approximately 930 C temperature, it becomes very hot and sticky, much like a stick of chewing gum. So the coefficients of friction are 35, 40, 45%, which makes it very challenging in the tool to properly form the part and also to protect the tool over the life of the tool. But material is very soft and flexible, which makes it ideal for making deep drawn parts. And that's where the biggest benefit of hot stamping process is, the ability to combine multiple parts into one deep drawn part, that's where people see the biggest opportunity for weight reduction, mass reduction, and cost reduction as well. So I'm going to talk about tooling today, and in the hot form tools, they're water cooled, and so the water cooling can present some challenges to making any die revisions once you build a production tool. So in some cases, we'll go ahead and we'll produce a prototype tool, and that prototype tool can be non-cooled, as in the example on the lower left, or it can have some simplified tooling as shown in the other photos. The purpose of the cooling is to cool the die down to a temperature that is low enough to be able to absorb all of the thermal energy from the blank as it quenches, so that you exceed that 27 C per second rate that was mentioned earlier. And that gives you a relatively trouble-free transition from austenite to martensite without any chance of having retained bainite. And so you can do that with a room temperature tool. Obviously, after you heat it up, if you try to put another part in there immediately, it's going to keep getting progressively warmer and warmer. So water cooling is primarily used to reduce the heat of the tool between cycles, to extract that heat from the tooling and to get it into a water chiller where it can be removed and then replaced with cold water to cool the next cycle. In some cases, the part geometry or the thickness of the material or the cross-section of the tool may be such that you need to use the water to get proper part quenching during one cycle, but that's relatively uncommon. Most of the time, what we're trying to do with water cooling is to cool off the die to improve cycle rate. If we didn't do that, we'd have to wait for a while between unloading the part and loading the blank to allow the die to cool off. So the reason we do some simple cooling on prototypes is simply for cases where we're going to make quite a few prototype parts and we don't want to spend the extra press time. In the production tool, it's much more complicated. The production tools have cooling channels that are developed to efficiently reduce or remove the heat so that we can improve production rate. The time required to load and unload the parts in a press is relatively constant and optimized, but the time that we leave the die closed and quenching is not. So anything that we can do to remove quench time will improve production rate. So this is an area that we in the industry spend a great deal of time on in order to optimize production. The first step in evaluating a process is simulation. And as was brought up earlier, the press hardening simulation is complicated because you are dealing with a number of different variables. Unlike cold stamping, where you're primarily dealing with the material, surfaces, geometry, and friction, in hot stamping, we have a lot of other variables involved. Not only do we have to do a simulation that validates the potential of making the part properly and forming it properly without splits or wrinkles or excessive thinning or residual stress, we also have to simulate the heat treating process. And so now that, and we have to do those both at the same time. So these are a lot more complex to set up and operate, but they have been developed and the process is relatively mature. Most commercial software can give pretty good prediction for press hardening simulation. The biggest factors, as was earlier mentioned, is to make sure that the simulation accurately reflects the die condition that you're going to have in the press. So the first thing we do, and all tool builders do this, is they spend a lot of time figuring out exactly what they're going to do with the tool. In this particular case, this part we were planned on locating it off of this 4-way locator pin, a 2-way locator pin, and a slotted hole in the blank. That gives us good control over the blank for through the forming process. Not great control, but good enough for what we needed. This was actually in the center of this part, and you'll see later this part gets split in half, and this center area is scrap. Most of the time when you put locators into parts that are being hot stamped, regardless of the type, the material is so soft that it will end up malforming a hole, and you'll put an embossment or a flange onto that hole if the part moves at all during forming. But the pins locate the blank, but we first start when we look at a part, we evaluate, do we want to hold water or not hold water, and invert it as you see here. And then we try to see if we can crash form it with no control pads or tools. In many cases, that's possible. In other cases, we find that we can't crash form it because of problems not so much with thinning, although sometimes, more often with wrinkling. And that's because of the high coefficient of friction on the parts that kind of is the reverse of a cold stamp process. So in this case, we felt that we would have wrinkling problems in this area if we did not have a pressure control pad. And in hot stamp, we use basically a force pad that can hold the part in position during forming, or we have a gap pad that provides a small gap to allow material flow. In this case, we looked at a 50 millimeter stroke pad with no gap to kind of lock the material on the post, and then the cavity would come down and form around that punch in order, or the die technically, in order to wrap the material around that form. The big forming area here is this particular area. So the next step, once we figure out how we want to control the part and what kind of tools we are going to use to control it and get our formability, is to evaluate material utilization. That's fairly straightforward, but you have the additional complication of laser cutting on these, so that has to be taken into account. Then we evaluate thinning to see if we have an acceptable level of thinning. Generally, the industry is working between 17 and 20% thinning as a maximum allowable thinning. In this case, you can see the outlines of the finished parts, and those are generally outside of the area where we're getting some thinning, which isn't too much, but it's still getting up into that 15% range. But that was considered acceptable, and so we were able to proceed with the project based upon those results. And we did find that we did not have any split issues in this area when we built the tool and went into production. Thickening is generally the bigger issue, and so we always are concerned about that. The metal tends to stick and bunch up, so in the event that we can't control the thickening, we get too much thickening, then we may have to use a different pad strategy. Instead of putting a pad over this area to control it, we might put pads on the outside and to allow us to control the wrinkle heights out in this area during forming. Instead, this level of wrinkling was not excessive, and so we were able to iron out those wrinkles at bottom of stroke, and so this was considered passing and below the threshold that we had set for wrinkling. The next thing we have to look at once we feel that we can form the part and not have splits and wrinkles is temperature quenching. So there's two things to be concerned about. First, you have to form the part before it gets too hard to form and starts cracking. So we look at temperature, and I'll go into more slides here next to go into more detail. But temperature quenching now is the final thing that we evaluate before we're able to proceed with the die design. We create a simulation report. In many cases, we'll go into die design. Then, because we're making maybe some changes during the die design, we may have to come back and do additional loops and do a second or third simulation after it's passed. So earlier I mentioned thermomechanical simulation. Basically, we're forming and extracting heat. We're also generating heat because as we form, we generate heat. And so we have to evaluate that. So a good thermomechanical simulation tool will be capable of doing that. In this case, what we're doing is at the moment we reach bottom of stroke, we'd like to know what the blank temperature is to make sure that it's above 400 C, which is where we start seeing very rapid transitions from austenite into martensite. So to the extent that we can keep the temperature up during forming, that's great. We want to make sure that we're fully formed before we start getting cold spots that start getting hard, like these points here. The reason these are getting hard is in this particular tool, we had pressure pads or force pads in these areas over the locator pins to help those pins hold the material in position. And so that started quenching out the material before the forming was accomplished. We also, through the simulations, help establish tonnage curves for pads and for forming. And those are important to help size the pad pressures and to come up with a minimum tonnage that we believe we should be able to form the tool in or form the part in. That helps us validate that the tool can run in a certain press, and also gives us a starting point for tryout to see if we can get to bottom of stroke with that tonnage. The last thing we really check is how, after we get the tool to bottom and it's properly formed, no splits or wrinkles, and we're didn't get too cold before we finish forming, is what is the quench rate? So we have a requirement to get below at least 200 C, optimally 170 C on material before we remove it from the die. Some parts are more sensitive to that than others, and but once you're below that 200 C, you should be fully martensitic. What you don't know is whether, if you take the part out and you finish air quenching on a cooling conveyor, whether that part's going to twist and give you some variation, and you may need to quench it for a longer period of time in the die to get it to an even colder temperature. So part of the simulation process is understanding the quench capability. If we're not quenching fast enough, we have to do something better with the cooling in the tool in order to accomplish that. Or we may have to increase the quench tonnage to accomplish that. Ideally, you quench with as little force as possible and as quickly as possible. That gives you the best possible die condition where you're not picking up any aluminum silicate residues into the tool that reduces the frequency of cleaning. So here you can see we're at very good temperatures after 10 seconds. This particular part didn't need to quench any faster than 10 seconds because the press that it was going into was very slow. And so this was a very acceptable simulation. And we found when we built the tool that that's exactly what happened. So when we build the tool, what we have to do is to take those simulations and determine, are those simulations accurate? Can we correlate to actual results? So we take blanks, we learn how fast we can heat them up by doing thermal traces on blanks with thermocouples. We then use that to set the amount of soak time in the furnace for proper alloying and to establish a minimum temperature or time at a certain temperature in order to properly austenitize, soak, and alloy the material. And then we set a maximum time that makes sure that we protect the coatings and the inner diffusion layer from excessive growth. And then that becomes the nominal process requirements for the first step in the process, which is heating the material and austenitizing it prior to forming. The second step in the process is the quench process, where we have to determine what's the minimum tonnage that's required to properly quench the part in the amount of available time or the desired time that, and we want to minimize that time and tonnage because it's beneficial to the tool. So all press hardening lines have data logging that capture all the temperatures and the times and the furnace dew points and the air times and the water flows and water temperatures and the blank temperatures and the part temperatures, the forces, and they generally do that in today's world by each press stroke so that you have the ability to have full traceability of any part to any process and process variation. That's an important part. You'll hear more about that in the seminar on Thursday. The big challenges in press hardened steel tools are the water cooled tooling. So we have these cooling channels that we put into the tools, and they're not easy to put in. We cross-hole drill them, and we try to keep the holes as small as possible and put as many holes in or channels in as possible. That's for optimum efficiency of transferring the heat from the surface into through the tool to the water channel and then into the water and out of the tool. But this adds a lot of complication to the design, as you can see. You know, it's easy on a simple straight part. When you get a part that widens out or narrows, your number of channels have to branch out or collect, and it adds a lot of complication. So there's a lot of fluid power engineering that we use in order to, or fluid transfer that we do to simulate that. That can involve computational fluid dynamics, which is used in some cases. We'll show you an example. But most of the time, the computational fluid dynamics is being used to ensure that we don't have air pockets. So we look at the flow and we see if there might be trapped air that we have to do differently. In other cases, we're looking to see that the flows of the water are balanced. And so we use what's called a fill cycle or simulation that shows the rate of time that it takes to fill a particular circuit, and we can compare those circuits to each other to see if the same flow rate can be achieved in parallel circuits. If you don't have balance in your circuits, then one circuit will take the majority of the water and the other circuit will get starved of water and it won't do an efficient job. Once we get that done with that, then we basically package the tool steel blocks into the die shoe. We make waterline connections as required, which can get complicated. Here's a 6 small blanks in this tool. You'll actually see this tool running in production next Tuesday. More commonly, though, you have a dual cavity arrangement or 4 cavity arrangement, and the water cooling connections from the cavities to the press are a lot simpler than what we saw in the last slide. So there's a variety of different ways to make parts. You can make them like this, where we're making a right hand and a left hand, or you can make duplicate parts and tools. We try to put as many parts under the press as possible so that we can reduce the cost of production. As long as we have adequate bed space and tonnage and furnace size capacity, we try to run multiples. That wasn't originally done in hot stamping, but it's quite common today, and it has significantly reduced the cost of processing parts. So when we select tool steels, we generally are using an H13 tool steel. It's through hardened. We need good thermal conductivity in the material to take the heat out of it and put it into the water. How the tool's going to get hot and cold and hot and cold, and so there's going to be a need for heat checking resistance. So there's a lot of different alloys available that you can choose from in order to tailor the tool steel to the requirement of the project. There's also special alloys available to solve special issues. However, we typically try to use one alloy in the tool all the way through it rather than combining alloys because of differences in thermal expansion and people mixing up steels when they may maintain them. Tool steel cost is a significant portion of the hot stamping tool, and it can significantly vary. There's some tool steels that are extremely costly compared to other tool steels, but in many cases, they're worth it for certain applications. Keep in mind that on hot stamping tools, you may need replacement blocks or pads during the tool life cycle. And the time needed to replace these forming blocks and taking the tool out of service often justifies spare or duplicate tools. So we have these channels, they're near the surface, we keep them small, flows have to balance, they can't leak. It's kind of complicated putting these in. We cut these tools into 3D finish shape with a little extra material, through harden them, and then final 3D cut if necessary to compensate for tolerances. That's the basic process for making the tools blocks. You have to be careful not to get too close to the surface. You have to allow for expansion of the tool without creating water leaks, and the machining has to be extremely precise. That's one of the reasons we got involved in it, is it used our skills in precise 3D cutting. There's a lot of wear on the male radii in the tools, and that slows down the quench. And so there's things that have to be done to compensate for that. And that's basically the discussion on tooling today. I appreciate all your time. Thank you for your attention, and I'll be happy to answer any questions.
Excellent, Mike. Yep, and I was just going to ask if you've got your contact info, which you do on that slide. So good. And I'm going to lead off with a question that relates to one of your last slides where you talk about die wear and how it affects the contact between the die and the part, and the quenching process. So do you want to talk at all about how you're maintaining the quenching process as the die wears and your contact between the die and the part becomes compromised?
Well, you can allow some extra material when you build the tools to allow for a recut on the tool. That's the most common process. The problem with doing that is it slows down the quench rate when the tools initially build. It gets better as you recut it,
Okay.
but that's the most common process.
Interesting. Good. Okay. We've got a few questions lined up, but we've got some time if you folks want to pose some additional questions for Mike. And I think we've got Danny and Eren around as well. So, Mike, supercooling on the sidewall. Can you talk about how you're accomplishing that? What technology you're using to get supercooling on the sidewall?
Well, cooling on sidewalls is one of the challenges. Normally, we try to keep 6-degree angles on the part in order to be able to create a force vector that puts some contact pressure on the sidewall. We add more cooling into the sidewall area than we do on the flats of the part, the horizontal surfaces. There are some cases where we can put a special feature in to create a side load of a tool to close that up. We also tend to reduce our clearances and increase our bearing in our sidewall areas.
Okay. I know during the demo next week, and I think our presentation on Thursday, this coming Thursday as well, we're going to talk about laser blanking, laser trimming, and I know you guys are using the laser trimming process. Are you seeing, or do you foresee application for pierce and trim dies with the hot stamp steels, or is that still not something that we're able to do?
Piercing in hot stamp tools is not uncommon. Most of the time it's being done to pierce a PLP hole into addenda on the blank in order to accurately locate the formed draw shell in a laser fixture for cutting. It's difficult to pierce, and if you're not doing direct pierce, if you're doing cam pierce, it's quite difficult. But if you're direct pierce, quite often you can tip the part to an angle where you can put in hot pierced PLP holes for laser. And although that is a relatively high maintenance area, if you otherwise would have to go through 2 laser operations, one to put in a PLP hole and the second to do the cutting and trimming, it's well worth it.
Good. Okay. Best roll direction of the material, specifically 22 manganese 5 boron for PHS blanks. Are you paying? I assume you're paying attention to roll direction, grain direction.
Grain direction can be important. It's not too critical for welding or other assembly processes, but there is some impact in forming. The formability, once we austenitize material, it tends to form, whether we're longitudinal or transverse, fairly equally. However, as you heat material, it expands, and as you quench it, it contracts. And we find that the grain sizes are oblong due to rolling, and so the blank tends to expand more in rolling direction than it does transverse. So once you make a part out of a certain rolling direction, if you're using developed trim on the part you're probably going to want to maintain that rolling direction, because if you turn the part in coil, it's going to shrink differently and give you different dimensions.
Great. So, Mike, at last year's hot stamping conference, which you also presented at, we had a speaker that talked about additive manufacturing of tooling for hot stamping, where you don't have to machine in the cooling channels. Have you seen any? Have you had any experience with that, or have you evaluated that opportunity to make the tools with additive?
Additive is being used in very limited cases in severe areas on tools where they have a unique problem that can't readily be solved with drilled hole cooling. So it's being adopted, but on a limited scale basis. It's generally a small section in a difficult corner of a tool where they have problem getting proper quenching in that area.
Okay. Okay. Another question on quenching. So what do you see as the biggest bottleneck, is the term the attendees using, to removing heat in order to decrease your quenching time? Is it removing heat from between the formed part and the die, or is it from the die into the cooling channels? What are the challenges in decreasing quenching time?
Well, first of all, a lot of people don't understand how to balance out the flow and pressures of the water chiller to the tools in the plant. Some people have older low pressure water chilling systems, and it's difficult for them to get enough pressure to get efficient heat transfer. We normally run at between 6 and 10 bar, 100 to 180 psi in water pressure in order to get good thermal transfer from the wetted interior of the cooling channel tube into the water. We also need to get high velocity turbulent flow, or we're not going to get good thermal transfer. So people have to look at the whole process from their plant chiller through the water piping lines out to their presses, and then through the tools itself, and work on optimizing that. And then, of course, that changes over time. The channels have to be cleaned. And so from a water perspective, that's one factor. The biggest factor, however, tends to be buildup of aluminum silicate coating on the tooling, not cleaning it properly. That causes separation and reduced contact pressure. We like to be at least 5 megapascal of contact pressure, ideally 10 megapascal of contact pressure. And once you start building up any accumulation of material, then you start reducing the contact pressure in other areas of the tool, and those areas start getting hot. That's why you put thermal monitoring on the parts coming out that can help you identify a part that's starting to come out hotter and hotter. That means you've got some coating pickup in there that needs to be cleaned out.
Gotcha. Okay. Just a couple of more questions, and I know we're a little bit over time here, but does the material have to be gauge controlled beyond standard typical levels in order to achieve uniform quenching? Do you have specific material gauge control requirements?
We're normally holding tolerances on the tool well under a tenth of a millimeter type tolerances. And so I think that normal ASTM tolerances give you so much variation that it becomes a problem for you if you have different material suppliers and your gauge is going up and down. It's going to cause a problem. If you have that problem, you need to use a specialized floating cavity process where you can compensate for that. But the most of the major mills today that are producing aluminum silicate coated material have quite good gauge control. And so once you are set up with a supplier and your tools properly spotted, you normally don't have too much of an issue with material variation unless you start changing to a different mill or supplier.
Okay, good. So you spoke plenty about the types of tool steels, but are you recommending any specific surface treatments on the tooling? Have you had much kind of trial and error with tool surface treatments on the tools?
Well, there's a lot. Most of the surface treatments that have been done have been accomplished by our customers, so we don't always experience that. It's usually due to the process. That's how it works in cold stamping as well. But we have some experience, and what we've seen is that although the coatings don't tend to change friction much, they do tend to reduce the amount of coating pickup and make it easier to clean the tool. So there's some advantages, but this is a pretty abrasive process, and so it's difficult to get a very thin coating to last very long. But if your main concern isn't protecting male radii and you're more concerned about the ability to clean material out of female radii and then in pockets and things, then it might be a good choice.
Okay, thank you. This one might be for you, Danny, or I don't know if Mike can answer as well. The maximum percentage of non-martensite allowed on PHS components.
Danny, I can take that. That depends upon the customer.
Hey, that's what I was going to say.
Yeah, there's some customers that'll say 100%, and they wink their eye knowing that it's almost impossible. There's others that have a specific percentage that they consider acceptable.
100%, exactly what I was going to say.
Good deal. And it looks like this will be our last question. What level of spotting the tool would be recommended to achieve the clench, in particular in sidewalls, Mike?
Well, as good as you can get. However, you want to do that in the home line press, which is going to have different deflection characteristics from a tryout press. So typically, we recommend taking the tool to a certain level of spot or bearing at tryout and then getting it to the home line press as quickly as possible. That doesn't mean that you might not take it back to try out and do some additional work there, because that's logically where you would want to do it. But you're going to want to take the spot results off the home line and then work the tool to improve it and then get it back to home line again.
Excellent.
I just want to add to that, something that's important is that if you are not having good contact and you're not reaching the critical cooling rate, if you don't develop the martensitic structure in that location, you're going to have different crash performance. So your quality control, if you are doing the hot stamping process, if you're responsible for that, your quality control must be sufficient to achieve the martensitic structure or whatever the targeted structure is by your customer in all areas of the part, not just the areas where you're doing your QC quality control checking. And differences in hardness or microstructure will affect the way that part behaves in a crash. and these parts are typically applied in safety critical locations. So just some extra comments there on the importance of doing proper quality control, quality assurance, and monitoring.
Well, thanks, Danny, for that. I mean, it's a perfect lead-in to our next webinar package, which comes up on Thursday, where we will be talking about process control and monitoring, and then we've also got a presentation on laser blanking. So that concludes the webinar session. I know we're a little bit over, but thanks for hanging with us. Part one of the three-part series. So part two is on Thursday, and then part three, which will include our virtual plant tour, is then again on next Tuesday. So I want to thank everyone for attending, and I definitely want to thank Eren and Danny and Mike for their presentations. We hope everyone found it to be valuable. And again, the archive recorded sessions will be available next week after the third session. We'll put them all up on our website, and we'll send you a link via email next week on how to access those. So then you'll be able to review again what you learned today and then share it with others within your organizations. So again, please join us Thursday for part two, presentations on laser blanking for supplying material to hot stamping lines, and then a presentation, as I noted, on process control and monitoring of hot stamping lines. So we'll see you on Thursday. You can go ahead and close your browsers now and enjoy the rest of your afternoon.